Okay, in the last video we talked about mathematical modeling. In this video I'm going to do an example of how we can use mathematical modeling to model the velocity of a falling parachutist. So, falling parachutist example. So we're going to use Newton's second law to develop a mathematical model of the forces acting on this parachutist, and then we're going to solve this mathematical model, come up with a solution. It's going to be in the mathematical model will be in the form of a differential equation, which we'll then solve using both calculus, and then I'll show you how numerical methods come into play and how we can use them to solve the mathematical model and get an approximate solution as well. So we start from Newton's second law. Newton's second law, which Newton's second law says that the acceleration of any object is equal to the net force on that object divided by that object's mass. Another way of looking at this is to say that the acceleration is equal to the time rate of change of velocity. That is, acceleration equals the first derivative of velocity with respect to time. So let's draw a little free body diagram here of a little parachutist. Okay, this is going to be the parachutist and his parachute. There's going to be some upward force on this parachutist. I'm going to label it as F sub u for F upward, and some downward force on this parachutist, F sub d. Now I'm going to draw my coordinate system in here like this. This is going to be y. I'm just going to call y for the vertical coordinate. I'm going to say the downward direction is positive and the upward direction is negative. So the forces include both gravity, which is pulling the parachutist down, and air resistance, which is working against gravity. So the forces include gravity plus air resistance. Okay, now we can model gravity many different ways. We could use Einstein's theory of relativity to model gravity, but it's a little overkill for this problem, so let's just use the Newtonian classical version for the force of gravity. So F downward is going to equal the mass of the falling parachutist times the gravitational acceleration, which g is equal to 9.81, approximately equal to 9.81 meters per second squared. And then let's model air resistance with a linear model for air resistance. So linear meaning we're going to set it equal to some coefficient, which is going to be the drag coefficient, times the velocity. So this is linear because it's not raised to any power. So c is the drag coefficient, and it has units of, sorry, we'll just ignore this, units of time. Oh no, I was right. Mass over time. So that's the units of the drag coefficient. Alright, now what we can do is we can plug these values back into Newton's second law. So Newton's second law again says the acceleration, which is dv dt, is equal to the sum of the forces, the net force. So we're going to have mg, which is the downward force, minus cv, which is the drag force, all divided by the mass of the parachutist. So we can simplify this and write it as g minus c over m times v. So this is our mathematical model for the falling parachutist, and it's a differential equation, so let's just write it again here. dv dt is equal to g minus c over m times v. This is a differential equation. Now we can solve this differential equation using calculus. So calculus can solve for v sub t, v as a function of time. And if we do this, I'm not going to walk through the details, but I'll write down the solution that calculus gives us. We have v sub t is equal to g times m over c times 1 minus the exponential of minus c over m times t. This is the exact solution, and it's an analytic solution. Exact solution. And it's also analytic. Analytic means you can write it down as an equation. So this is an equation. That's why it's analytic. Now let's look at what this solution actually looks like if we give some numbers to the mass here and the drag coefficient and the gravitational constant. Okay. Here's a little diagram showing our falling parachutist, and here is a plot showing the solution, the exact solution to our mathematical model for Newton's second law for this falling parachutist. If we give him or her a mass of 68.1 kilograms and a drag coefficient at 12.5 kilograms per second. So we can see that he approaches some terminal velocity. It's around 53.44 meters per second. And you can actually figure that out by taking the limit of that solution as time approaches infinity. Alright, so we've solved our mathematical model. Hooray, and we've used calculus. Now, I said that we were going to talk about how we could solve our mathematical model problems numerically. So first I want to talk about why we would want to do that. First of all, one of the first reasons is this solution, this exact solution, is only valid for one set of parameters, c, m, and g. So, for example, if c, m, or g change, then our solution is no longer valid. Then our solution is no longer valid. And we have to come up with a new equation for our exact solution. Now this can be kind of cumbersome if we're trying to model real-world behavior, because falling parachutist, their drag coefficient isn't going to remain constant. When they jump out of the airplane, they're probably going to have some maybe spread eagle posture, and then maybe after some time they will pull their arms in tighter to their body and their drag coefficient will go down, they'll become more aerodynamic. Or maybe the opposite, maybe they'll be very aerodynamic and then want to slow down, and so they'll kind of spread out and give themselves a bigger cross-sectional area and slow themselves down. Mass could change, not very likely. The gravitational constant definitely changes throughout their fall, not very much, so this might be a good enough approximation for our case. But the fact is parameters change a lot whenever in the real world. Real engineering problems, we have to deal with those types of things. And it's easier to deal with them numerically. The other reason, and this is probably the bigger, more important reason, is that most realistic problems don't actually have an analytic solution, meaning they don't have a solution that you can write down in the form of an equation. They just calculus, we don't know how to solve for analytic solutions for them. The number of analytic solutions that exist really only exist for simple cases that we can use to kind of illustrate, like this one. So most real world problems or more complicated mathematical models that represent them don't yield analytic solutions. So that's the case. What are we going to do? Well, the answer, of course, is numerical methods to the rescue, right? Numerical methods to the rescue. So that's what I want to show you. I want to show you how we can take this problem that we just did and use numerical methods to come up with an approximation to the solution. Whoops. Alright. So let's give us some space. Alright, so what we can actually do is we can go back to our differential equation, which was dv dt equals g minus c over m times v, and we can approximate this derivative dv dt using what's called a finite divided difference, or a finite difference approximation. So we can take a finite difference or change in v and divide it by a finite change in t instead of an infinitesimal change in v compared to an infinitesimal change in t. These are the infinitesimal changes. These are finite changes. So we can literally write that as v at some value of t, I'm going to call it ti plus 1, minus v at ti, all over ti plus 1. This I plus 1 and I, these are subscripts, minus ti. Now, what does that mean? Let's draw a little picture here of our velocity function to help you better understand. So this is time, and this is our v sub t. Now what I'm going to do is just mark some values for t. We'll call this value of t ti, and this value ti plus 1. And let's draw our function here. Let's say our function looks something like this. So now we can actually say, okay, this right here, this is v sub ti, And this right here this is v sub ti plus 1. So what we're trying to do is we'd like to approximate the derivative at v sub ti. So the derivative is literally the slope of this tangent line that touches this curve right here at ti. That's the true derivative. But what we're doing up here is we are approximating the derivative by saying, hey, let's take a line in between these 2 points, a secant line to this curve actually, and let's say that the slope of this line is actually, we're going to use that to approximate the derivative of v sub ti. So that's what we're doing up here in this, we call it a forward finite difference approximation because we're using a point that's in front of or in forward of the point that we're interested in, ti. So let's take that finite difference approximation and plug it into our differential equation right here. So we're going to take this and plug it in right here. So if we do that, this is what we're going to get. We're going to get v sub ti plus 1 minus v sub ti all over, I'm just going to call this delta t down here, is equal to g minus c over m times v at ti. Alright, so now what we can do is we can solve this equation right here for v sub ti plus 1. And I'll show you when we do that, we get the following. V sub ti plus 1 is equal to v at ti plus g minus c over m times v at ti all times delta t. Now this right here is what's called the finite difference solution to our differential equation. And we can use it to generate an approximate solution of our differential equation. Let me show you how we do that. So we know when the parachutist first jumps out of the airplane, he has no initial downward velocity. So we know v at time t equal to 0 is equal to 0. And we can also just label that v sub 0. Now what that looks like on our little velocity plot is something like this. This is v sub t. We know at time t equals 0, the velocity is equal to 0. So what this finite difference solution to the derivative allows us to do, it says, if you know it at some time ti, say you know it at time t equals to 0, you can now find your velocity at some other time. So v of t plus delta t. So we can figure that out using this equation. So if we use, let's just say for example at delta t, here let me go back up to this plot up here. This right here, let's call this interval right here of time delta t, okay? So that's delta t. So let's say delta t is equal to 2 seconds. We want to find, we know there's velocity at time t equals 0. Let's find delta t at, let's use 2 seconds. So what I'm saying is down here, I'd like to know the velocity at time t equal to 2 seconds. So what I can do is I can say, well, the velocity at time 2 seconds. It's just going to be equal to, I'm going to use this equation, this 2 seconds is our ti plus 1. It's going to equal our velocity at time 0 plus g minus c over m times v at 0 times our delta t, which is going to be 2 seconds. Now I can plug in values for g and c and m, and I know the velocity at time t equals 0 is equal to 0, so I can plug all those numbers and actually get an approximation for the value of v at time t equals to 2 seconds. It might be something like this. Well, this is now v at 2 seconds. Well, now what if I wanted to continue and get an approximation for v at 4 seconds? Well, now I can just use this equation up here and plug it in. So v at 4 seconds is going to equal v at 2 seconds plus g minus c over m times v at 2 seconds times delta t, which is 2 seconds. And I'll get some other value up here for v at 4 seconds. So now I've computed a value for v at 4 seconds. Well, I can just continue this process to get v at 6 seconds, v at 8 seconds, so 6 seconds, 8 seconds, and so on, and I can do this as many times as I want to get this approximation. This is an approximation to our differential equation describing the falling parachutist velocity. So the handy thing about this numerical solution is it's very easy to teach a computer how to do this, and you can change the parameters at any given time during the solution. So maybe to here we use one set of values for m, g, and c, and then here we change those values, and then we get an appropriate solution that, or an appropriate approximate solution that reflects the new changed values. So let me go ahead and show you what that looks like. So here we've got our finite difference approximation to our differential equation, and here I'm showing the actual plot of the exact solution in blue, and the numerical approximation is these red dots and corresponding lines. And so you see that there is some difference in the approximation and the exact solution. There's some error, but it seems like the numerical approximation at least converges to the same general terminal velocity as the exact solution. And over here this table is showing the actual computed values for these red points, so at the different time values. So cool thing is hey, guess what? If we want a better approximation, one thing we can do is we can make the time step smaller, and now look how closely it fits. It fits much closer. And like I was mentioning before, if we change the parameters, say we change the drag coefficient at time t equals 20 from 12.5 to 9.5, well, we can see how the velocity changes in our solution very easily. Anyways, now you can kind of see we've kind of covered an example of how you would use numerical methods to solve a mathematical model, some differential equation. So in the future lectures we're going to kind of talk a little bit more about the error in numerical approximations. We showed here that by making this step size smaller, this delta t value smaller, the error went down. Why does it do that, and can we quantify that? And then we also saw that just in general, there's this error. How do we quantify that? We can take the difference between the exact solution and the approximation. But what happens when we don't have an exact solution? We'll talk about that. How do we get an approximate error, or a way of estimating how big the error is? So those will both be topics that we'll hit in future videos. I hope you've enjoyed this video, and we'll see you in the next one.